Afternoon, or good morning, or good evening. We're delighted to have such a great audience joining us today from such a wide areas from around the world. Welcome to the spring meeting of the National Academy's Committee on Earth Resources. My name is Jim Slutz. I'm the chair of the committee. I'd like to just say a few words about our exciting program today, cover a few housekeeping items, introduce our committee before I turn things over to John Marsden, a member of our committee who will be serving as moderator for today's webinar. First, let me just for anybody that's new to the committee, let me just share that the Committee on Earth Resources was established in 1991, so this is our 30th year. It is the standing committee of the Board on Earth Sciences and Resources and serves the community by monitoring and engaging on issues relevant to energy and non-fuel mineral resources. The committee examines issues related to the availability, supply, delivery, and impacts of energy and mineral resources, the health and safety of the workforce engaged in resource exploration and production, and the management and stewardship of the lands on which they are located. The committee serves stakeholders with objective, evidence-based scientific and engineering information to help support decision and policy making. Our committee has been working on the issues related to minerals, critical minerals, and energy resources for many years. As we began discussing our virtual spring meeting plans earlier this year, we thought it was timely to draw these themes together. The need for mineral resources to support the energy transition as we look toward ways to address climate change. As John will describe to you, we've organized the meeting into a three-part webinar series, with today's kickoff webinar helping to put into perspective different aspects of minerals, critical minerals, and the global and domestic supply chains related to energy infrastructure. We hope you'll be able to join each of the other webinars as well on May 17th and June 1st, because we've arranged them to build upon one another and will all benefit from audience participation throughout. Now, let me say just a few words on how you can share your questions and ideas today. For our committee, you'll be able to raise your virtual hands on the Zoom, and John will call on you when we move into the Q&A part of the meeting. For those of you in the main audience of the webinar, you may share your questions or comments by using the Q&A function at the bottom of your screens. You can simply type your questions into that box at any time, and the staff team will keep track of the questions and share them back to John as he moderates. And he'll keep the conversation moving with panelists and the committee. Please participate. These sessions are they're intended to be interactive, and we count you as part of the discussion and equation in this meeting. And in addition, we will be posting the webinar recording on the committee's website, and we'll let you know when that's available, probably in about a week or so after this meeting. With that, let me introduce our committee members, or Claire, let me have them introduce themselves briefly with their name and affiliation, and we'll ask them to turn on their cameras and unmute as I call upon them. So we'll just run down the list quickly. Bridget.
Hi everyone, I'm Bridget Ayling. I'm an associate professor in the Nevada Bureau of Mines and Geology at the University of Nevada, Reno, and also director of the Great Basin Center for Geothermal Energy. My area of interest and research is understanding geothermal systems. How do we explore for them more effectively and develop them in a sustainable fashion? Thanks, Jim.
Thanks, Bridget. Dan?
Hello, everyone. I'm Dan Connell, Senior Vice President of Strategy with Consol Energy out of the Pittsburgh, Pennsylvania area. We are primarily a coal producer, but a big part of my role is working on new technology development in mining, energy, carbon products, and other earth resources.
Thanks, Dan. Doug?
Thanks, Jim. And I'm not going to turn my camera on since I'm in a car for the next 5 minutes. I'm a consultant with Milroy Howlett Technology Partners. I'm a geologist by background with experience in mineral resources, geothermal energy, and long career in the oil and gas sector. So experience also both in the federal government and in the private sector. Thanks.
Thanks, Doug. John Leftwich? John, I think you're muted. Okay, let me go on and then we'll come back around to John. Deborah?
Thanks, Jim. I'm Deborah Peacock. I'm a metallurgical engineer and a patent attorney, and I'm on 2 public company boards, one a copper mining company and another a graphite processing company, both of which are important critical minerals for the energy transition. And my background today is 0.999% pure graphite. So I thought that would be fun for this seminar. And I'm also on the chair of the Regents at New Mexico Institute of Mining and Technology.
Super, thanks, Deborah. Ann?
Thanks, Jim. I'm Ann Robertson Tate. I've worked at Geothermex, a geothermal consultancy, for almost 36 years. Started out in the geothermal industry, and here I am. I'm a geologist by training. Very interested in developing conceptual models of geothermal systems from multidisciplinary data, and also very involved in women in geothermal. Thanks.
Thanks, Ann. Tamika?
Hello, I am Tamika Cersei. I am a petroleum system analyst for BP, which is based in the UK. I live in Houston, Texas, where I assist with petroleum exploration and production via geochemistry and basin modeling.
Thanks, Tamika. David?
Well, I'm David Spears. I'm the state geologist of Virginia based in Charlottesville, Virginia. And as state geologist, I'm largely an administrator, but I have a science background. I'm a petroleum geologist. Early in my career, I worked in the petroleum industry. And now I'm involved in a little bit of everything: geologic mapping, mineral resources, and geologic hazards.
Thanks, David. John Leftwich, let me come back around to you if we can't see if we can, if you're able to connect. Okay, I'll take a stab, and oh, are you there, John? Okay, John, go ahead.
Yes, I am. My name is John Leftwich. Spent most of my career as a petroleum geologist, Exxon, Shell, and other companies in the Gulf Coast. And I have spent time teaching structure and tectonics in Old Dominion University. So I'm pretty much interested in all aspects of geologic sciences. So here I am. Basically, I'm pretty much retired now, but I'm interested very much in all the new things we're about to do here in the coming years.
Thank you, John. So we have one more committee member to introduce, but before I do, I would be remiss. I just wanted just a quick thank you to the National Academy staff, Elizabeth Ada and Calla Rosenfeld and Eric Edkin and all those others that are helping that we couldn't make this work without. Now let me turn and the program. Let me introduce John Marsden, also one of our committee members. John is going to be our moderator today. John Marsden has been the president of Metallurgium since 2009. John has had a long career in the mining industry, and with a significant stint at Freeport-McMoRan, where he finished out as president of the company. And so John has had a variety of different positions in the mining industry, as vice president of technology and development, or manager of operations. And he is very notably, he is a member of the National Academy of Engineering. So I'm very pleased that John's going to take over, and we have somebody with great expertise shepherding the program today. So John, I'm going to turn the question over, or the program over to you.
Yeah, thank you, Jim, for that kind introduction. And welcome everybody to the webinar. I'm going to run you through a little bit of background before we get to our speakers. And next slide, please. So the objectives of the webinar series is to look at mineral availability across global markets, and we want to discuss what needs to be done now and in the future to facilitate access to the availability of minerals. So we've got a forum. This is intended to be a neutral forum for an exchange of ideas and information across a broad range of sectors. And of course, to look at potential areas for further examination. Next slide. So this webinar today is intended to be an introductory series and looking at what are critical minerals and the practical needs for minerals in energy systems and infrastructure. And it's not a US-centric view. We're looking at a global view here. Next slide. So we've got 3 speakers this morning, and I'll be introducing them immediately before they speak. We've got each of them giving a presentation for about 12 to 14 minutes, and then we're going to have a panel discussion for the second hour of the webinar. Next slide. We've got 2 more webinars planned, one on May 17th, where we'd be looking at the US mineral endowment and sourcing alternatives and new approaches and technologies for extraction. And we've got 4 excellent speakers lined up for the second webinar session. And then the third webinar would be on June the 1st. And this would be looking at the regulatory, legal, environmental, economic and policy challenges and opportunities related to the supply chain, and particularly looking at barriers to bringing critical minerals to market. The speakers there will be finalized at a later date. Next slide. So this brings us to why now? And the National Academies have previously published an excellent document, but it's now 13 years ago, on minerals, critical minerals in the US economy. And in many ways, that was a very forward look and prophetic document. Since that time, we've seen an increasing number of very significant publications on the role of minerals and metals for a low carbon future. And I'm not going to go through all of these, but you can see that in the last few years, there's been a massive amount of interest developed. Next slide, please. And of course, in just the last month and a half, 2 months, we've seen some pretty significant moves and discussion, both in the news and in other forums, about the importance of metals and minerals as we move into an energy transition. And most recently, of course, last week was the announcement with the target to reduce greenhouse gas emissions in the US by at least 50% by 2030, which is a major target here. Next slide. Before I turn over to the first speaker, maybe just give a little bit of context here and discuss a little bit what are critical elements. And this is a particular classification developed by the American Physical Society recently. And this shows their view of critical elements broken down into convenient groupings, but the colored elements have been identified as critical elements. The point here that critical elements are different in different jurisdictions functions into different entities. And they can be viewed very differently depending on your particular perspective. And the next slide shows a different view, which is the American Chemical Society, their view, and they've classified elements as limited availability or rising threat from use, and then a serious threat within the next 100 years. The point here is that there's a significant number of elements that are viewed as critical by different jurisdictions, and there's a huge amount of overlap amongst these elements. Next slide. And finally, just this is an excerpt from the USGS looking at requirements of elements in integrated circuit chips, in computer chips. And the reason this is important, in the 1980s, there were just 12 elements required. In the 1990s, it increased to 16. And in the 2000s, we're up now around 57. So 45 elements more than were required in the 1980s. And this in many ways reflects this energy transition. And so with that, I'm going to introduce our first speaker, and it's Karen Hancoy, the director of the British Geological Survey. She's got degrees from the University of Copenhagen, including a PhD, her honorary doctorate from Uppsala, and her prior roles listed down here, but she's done a large amount of research at various institutions, both within Denmark and also at Woods Hole, Colombia, and has been a consultant to the mineral exploration industry. So with that, I'll introduce Karen.
Thank you very much, John. It's a great honor to be here. It's great to get the honor of being the first speaker on this excellent series of webinars. I think that it will be incredibly interesting, and I really like the way it's structured, with sort of starting with the rock, and then we are ending up and talking a little bit about how society is going to have to respond to some of these really important issues. I'm going to share my screen. There. I hope everyone sees that. And so basically, being the first speaker, I get sort of the privilege a little bit of waving my arms around and talking about the big picture of things. And so my semi-lame title reflects that a little bit: Minerals and Metals in the Energy Transition, Criticality, Demand and Supply, and Circular Economy. And I'm not going to cover any of those in great depth, but I'm just going to introduce a little bit some of those concepts that we need to talk about when we talk about how Earth resources are going to enter into the energy transition going forward. And so John introduced this as well. This book from 2008 by the National Academy of Science was really, I think, a milestone in the way that we think about this and the way we discuss it, and also in the way that that earth sciences are sort of engaging with this whole discussion. But basically, there were 6 objectives to this study when it was commissioned back 10, 15 years ago. And it was identify critical minerals and mineral products, excuse me, assess the trends in sources and production status of these minerals, examine the potential constraints. I mean, what's actually sort of playing into this? Is it geology? Is it economy? What is it? Identify impact and disruptions in the supply, describe and evaluate the current level of information for decision making, and identify types of information that may be needed to better understand that. And this was the figure that was really used to do pretty much all of those things in that study. It's a very simple idea and concept, but it really has tremendous sort of power in dealing with this problem. Basically, what you see on the left is the principle that on the y-axis you have the impact of supply restriction. How important is it? How bad is it if you can't have it? And on the x-axis you have the supply risk. What is the chance actually that there is going to be a limit to supply? And on the right-hand side, you see basically the result of a very careful analysis of this, trying to quantify those two ways of looking at different minerals. And you can see here on the right, the 11 elements that were studied in this particular study, including some mineral groups such as the rare earth elements. And as you can see here, for example, not very surprisingly, something like copper, tremendously important. So if we couldn't get enough of it, it would be a huge problem. But the supply risk is actually not that great because it's something that's being produced in many different places. So basically, this mapped out the study, the different elements and how we could think about criticality. And these are some of the conclusions that came out of this study. And the ones that I perhaps think are sort of most important for the discussion here today, and maybe especially the two first ones: all minerals and all mineral products could become critical. This is really important. And also, a critical mineral is both essential in use and subject to the risk of supply restriction that was shown in the figure before. And criticality may change as technologies evolve and new products develop. And that is also really, really important, because what that actually tells us is that why we need to talk about criticality and find solutions to criticality, we really should talk about minerals in general, because we don't know what's going to be critical tomorrow. And as John just showed now, there's also different criticalities for different sectors. So criticality is a hugely elastic and relative kind of term. And so it's important that we're very precise about what we want out of it. Very importantly, the restrictions on supply, so that x-axis in the diagram is typically due to significant increase in demand, thin markets, production concentration. So is it all produced in one country, for example? Production as byproduct, or lack of stock for recycling and or infrastructure required for the recycling. Also in the conclusions that over the longer term, these were sort of the restrictions of supply in the short to medium term. In the longer term, availability is really largely a function of investment, like pretty much everything else in this world, including, of course, the investment in understanding this, so the education and the research that goes into it. Decision makers need continuous, unbiased, and thorough information, and more information needs to be collected, and more research needs to be conducted on the full mineral cycle. So not just where can we find these metals and minerals, but actually how do they move through society? How do we understand the full cycle? So that was sort of a summary of criticality. And again, remembering that almost anything could become critical. This figure here is just really to illustrate why minerals as such, why are minerals really important? And they are, of course, important because we use them for everything that we do. And when we talk about the critical minerals, or the minerals that we need for the energy transition, you can also see them in this diagram here. You have a wind turbine in the background there. You have lots of transportation on here, getting that green, getting that electrified. It all requires different types of raw materials. And so sort of a Europe-centric view here again of why is this so important. But basically in Europe, there is not a lot of primary production of metals and minerals. But once you start moving downstream in the value chain into the sort of manufacturing, the processing industries and the actual manufacturing, the industry, the Apples and Audis of this world, then you see that the number of jobs and the value added to society is increasing tremendously. These figures are from JRC and probably almost 10 years old now, but still very valid. And interestingly, again, we can put almost any sector sort of superimposed onto this. And it will be true for all of them. They all actually start with the raw materials that go into the products that are produced. So again, it all starts with the rock, starts with identifying the minerals, finding the minerals, mining the mineral, and then we have a whole value chain that comes after that. And so if you look at it historically, where do we get the metals from? If you go back more than 100 years, almost 200 years now, the main producer in the world was Europe, here in the blue stippled line, overtaken by the United States around 1900 and up through the World War years. But from around 1970, several other regions across the world are coming in to the production, so that we today see a much more balanced, you could say, production actually across the world. But quite interestingly, You see Europe and the United States at the bottom now. So around now, we are down to, in Europe, down to something like 3 to 5%. We're consuming perhaps 15 to 20%. And or maybe even higher than that, I think 25 to 30%. And similarly for the US, we are down at around sort of 5% of the global production, but as we all know, a much, much larger proportion of the actual consumption or the use of metals. And this, of course, creates import dependency. And import dependency alone does not make something critical, but it's one of those things that can play into criticality, because if it is import dependence from areas that are, for some reason, subject to geopolitical turbulence or monopolies, then it can actually become a risk. And here what we see is the import dependency for Europe for a variety of elements. And you can see sort of out on the right-hand side, you have iron ore, zinc and copper, chromium. So some of the ores that we've been using for a really long time. But on the right-hand side, you see a lot of these specialty metals that actually go into new energy technologies. And as you can see, for Europe, we have an import dependency of 100% for all of these. So this is a huge issue that sort of means that we have to look at how we're going to make sure that we will have a secure supply. And one of the solutions, if you Google circular economy and images on Google, this is what I did here. And this is just a tiny, tiny sort of field of view from what comes up on Google. You literally get hundreds and hundreds of things that look like this. Many of these are sort of ways that we think about circular economy. Many of them are green because that makes them look more attractive. Many of them are completely closed loop. And it is brought forward as one of the solutions to securing mineral supply. Let's close the loops. Let's recycle so that we can just get everything that we need from things that we already have in the products that we are using. And so is this actually a viable option? And of course, there's two things that sort of mainly enters into this. And one is, what is actually the demand of what we need? And the second one is, how good are we actually at recycling? And I'll say just a little bit more about those two. So demand. What we are seeing is that we have a population increase across the globe. And so while it is still uncertain exactly what this is going to look like going forward, it is pretty certain that we're going to be more and more people. And not only are we going to be more and more people, we actually also use more minerals and metals per person historically. And this is a figure out of Gradel's group at Yale University. And what you can see here is that around 1900, there was, if we normalize the use of certain metals at that time, and then look at how much we're actually using today on the y-axis on a logarithmic scale, what you will see is that there's maybe a handful of minerals that we're using almost the same as we did 100 years ago, things like lead, silver, and tin. But if you look at a wide variety of other metals, again, for example, iron, zinc, and copper, we are looking at between 5 and 10 times as much per person, remembering that we are 3 times to 4 times as many people today as well as we were back then. So the demand just out of the sheer volumes that we're all using is a huge, delivering a huge demand increase on minerals in general. John sort of alluded to this as well. Another thing that plays into this is, what is it we're using then? Well, if you go back long enough, we just used flint. But when you go back, 300 years, 400 years, we were using metals, but we weren't using very many different metals. And as our technologies have become more advanced, we are using more and more different metals. And on the right there, you can see we're pretty much using the entire periodic table, as John also pointed out today, and we're using them for these energy technologies. And quite interestingly, of course, if we didn't use it before, it's not actually going to be there for us to recycle. And if you look at the energy transition, that's exactly what has happened. What we want to do is we want to go from a brown economy of combustion type energy technologies to a green economy where we have functional materials and e-motors and energy storage and energy conversion. And we're looking at those elements that you saw, that import dependency as well. It's cobalt, it's lithium, it's the platinum group metals, rare earth, and so forth. So there is an enormous need for these metals today, and we didn't have that need if you go back just 20 or 30 years. And this illustrates that, and this is out of the report that came out of the World Bank that John also mentioned. And as you can see on the left here, you have a variety of metals, again, in sort of the vertical column, starting with aluminum and ending with zinc. And then you can see sort of boxes checked against different energy technologies at the top here. And you can see where we need the different types of metals and minerals, and we need them a lot. And in this study, they've also looked at what do we think actually the demand is going to be as we move forward. And looking towards 2050, this is only 30 years away, this is what it looks like for those exact same elements. What we're seeing here is an increase, for example, for something like graphite, lithium, and cobalt of more than 400%. So 4 times as much demand as we have today for those metals. And even the ones where we're not predicting very large increases, we are talking about increase in demand of all of these metals as we go forward. The other aspect of the circular economy, of course, is how good are we actually at recycling? How good are we at retrieving the metals that we're using? And again, I want to go back to Gradel's group, and I'm going to try to go through this one fast. One can speak about this one for 20 minutes alone. But basically, what Gradel's group did was they looked at pretty much the entire periodic table, not everything, but many metals in the periodic table, and they looked at what enters into production manufacturing. That's seen here in the dark blue. Of that, so that gets into products, how much is actually going into real products and what is actually sort of lost off to the wayside here. And that's the next blue color you have here, in use products. So these are our cars and our computers and our everything that we're using. Then onto the next blue, that's actually what is potentially recyclable. What can we actually recycle? Because there's things we can't recycle. We don't have the technologies to recycle them or the means to actually collect them. These are things like rare earths and polishing materials and aluminum and steel making. So of what actually enters into the production stream, it's only a portion of it that we actually potentially can recycle. And how much do we then perhaps recycle because we are recovering it? And that is sort of shown here in green. So again, we're losing a lot to our drawers back at home and putting things into the wrong bins when we're actually trying to collect our waste. Also, what's missing on this figure, of course, I'm a geologist, is the mining. And if you know about mining, and you could hear a lot of the people certainly in the panel here knows about mining, this is the place where we introduce an enormous amount of waste. There's always going to be a waste rock. There's going to be rock that has lower concentrations than what we're wanting, and we're not going to process that. And so a lot of material actually gets lost already in the mining phase and in the tailings when we're doing mining. This is the result of the study coming out of this back from 2015. And as you can see, there's a lot of metals here in blue, which are the ones that we're actually fairly good at recycling, again, potentially recyclable. But there's also quite a lot of yellow on here. This is the stuff that we cannot currently recycle. So a lot of the rare earths on here, as you can see, and a lot of other specialty metals, again, these are the ones that we want so badly. We're actually really, really bad at recycling them. And when you look at what we actually do recycle, that is actually reflected in the numbers here. This is coming out of a resource panel, a UN resource panel report from 2011, and it has not improved very much in the 10 years since. We are pretty good at the ones that were also blue in the other figure, but the reds on here signify that we are actually only recycling up to 1% of something that in some cases we're going to see doubling or tripling of the demand of those. And finally, I want to return to this figure as well, because back to this thing of what we're using now, what we're using in the past, part of the circular economy concept is also that we want to design things for reuse, and we want to design things to last for a long time. Well, if we're designing a wind turbine to last for a long time, it's not going to be available for us to recycle for a long time either. So as long as things are in stock and as long as we're using them, they're not going to be available for us to recycle. This is a recycling plant in Ghana. And so just sort of to summarize that, even though we have this tendency to sort of want to see things as closed green loops and thinking then we can all support it and then we can all be for it, it's actually not that simple. It's extremely complex how we're securing our access to minerals, and especially the minerals that we need for this energy transition. So rather than think about these closed loops, I'd like to advocate for this way of thinking about the raw material value chain, the mineral value chain, and the circular economy. We do need to get things into the loop. Even if we had a case of a falling demand of something, we at some point in time, we had to put them into the loop by extracting them from the ground. We should not lose sight of that. And we should continue to have the conversation about how that portion of the value chain can become more sustainable, and what we need in this part of the value chain to be able to secure the green transition that we actually want. So we need to focus on this as well. We need to focus on the entire understanding of the value chain, going from the exploration and mining into processing, into the design and production of things, as I mentioned before, into the use, into the collection, into the recycling. And we need to acknowledge that there's leakage along this entire value chain. There's waste everywhere we go. People talk about zero waste, but in reality, it is almost impossible to imagine that we can do that. But we need to look at where we have waste and where we can minimize waste. So this is how I like to advocate for us to be thinking about securing the supply of this. And I'd actually like to just throw in there, maybe for the discussion, that what about these guys here? I mean, in the past, it's only been, the geologists and the miners up here that worried about where the raw materials came from. From these guys down here, again, the Apples and Audis and Siemens, for them, they've been buying it off the shelf at market value, and they have not necessarily paid too much attention to where did it come from and where's it going. Actually, there's been good business model in designing something for breaking fairly quickly, so that you'd have to buy a new one. What if we can get these guys to take some responsibility for the sourcing of raw materials and also for the recycling of raw materials? Then I think we have some chance of really talking about a sustainable supply chain for everything that we need. And we do need a sustainable supply chain for this reason here. Again, the one we'll be talking about very much in this webinar series is the affordable and clean energy. That's what we want. We're going to need raw materials to go into that. We're going to have to talk honestly and openly about the complexity of getting them there. So with that, I'm going to say thank you for listening. Thank you.
Yeah, thank you very much, Karen. Excellent presentation. Really, really interesting and stimulating. So now we'll move on to our second speaker. That's Nadel Nassar. And Nadel is the chief of the material flow analysis section of the National Minerals Information Center of the USGS. He's got a BS in chemical engineering, his MBA in sustainable global enterprise from Cornell, and a PhD from Yale. He's a member of the US National Science and Technology Council's Critical Minerals Subcommittee, and he significantly was the 2019 recipient of the Presidential Early Career Award for Scientists and Engineers. So welcome, Nadel, and please go ahead.
Great, thank you. Thank you for that kind introduction and for the opportunity to share some of the research that my group and I have been doing at USGS. Let's see if I can get this going. Okay, so I'm really fortunate to be here and talk to you about this, and also to follow up from Karen's presentation, because I think it really builds off of that discussion. So I'll just briefly talk about the demand side, but then quickly jump into talking more about the supply side. In terms of demand, for mineral commodities are really essential for both conventional as well as renewable energy technologies, including solar photovoltaics, as we talked about, wind turbines, especially offshore wind turbines with the rare earths, but also things like oil drilling with barite as oil and gas drilling muds, and as well as petroleum refining, such as platinum and rhenium as reforming catalysts. Gas turbine blades, they require super alloys for industrial gas turbine blades, and they require a number of different alloying elements there. And of course, the technology that everybody's talking about with electrical vehicles and energy storage with lithium ion batteries, really probably one of the largest, if not the largest transition that's going to happen to the energy system in the last few decades. And this is obviously a big deal for mineral commodities and the demand for mineral commodities. A lot of the concern, however, is on the supply side. And the reason for that is because production for mineral commodities is highly concentrated in a few countries. And so you have countries like Brazil that dominate niobium production. South Africa dominates the platinum group metals. Chile is a dominant player for rhenium. DR Congo for cobalt and tantalum. Australia and Canada provide a lot of different commodities. And China, I think, is the big story, producing much of everything else. And if you look at this data over time, what you see is that this is a relatively new phenomena. So this is showing China's share of global production, primary production of various mineral commodities. You can see things like the rare earths have been dominant since the 1990s. This is showing time series from 1990 to 2018. Antimony, same, tungsten as well. But for some of the other commodities, their share of global production has really increased just over these last couple of decades, including magnesium metal, gallium, and cobalt refining. And so, as was alluded in the previous presentation, what this has resulted in is many developed countries are increasingly import reliant. So this is a metric of net import reliance that our center has been measuring for many decades. And when you look at the number of commodities for which the United States is at least 25% import reliant, meaning at least 25% of US consumption is based on foreign imports, that number has increased from 21 commodities in the 50s to almost 60 commodities today. Now, in a recent executive order, we were asked to examine, well, where are we what's our foreign reliance? Where are we getting these mineral commodities? And that's what's shown in these three different periodic table figures, with the overall periodic table figure shown in the three colors. So we get a lot of mineral commodities either from domestic sources or from what Department of Defense calls security supply countries. There are a few commodities, including the rare earths and many of the metalloids that are used in, for example, solar photovoltaics, that we do get from what Department of Commerce labels as non-market economies, namely this is China. And then we get some of the other commodities from elsewhere. And so you might, the viewer might look at this and say, well, that's not too bad. It's just a few, commodities. But what this picture does not show is the import reliance on semi-finished and finished goods, right? So you might be importing a flat panel display or a finished vehicle, and that would not be shown here. Here, it's really talking about the raw materials. And so we're investigating this embedded demand to understand our foreign reliance more completely, to understand the dependency on not just the raw materials, but raw materials contained in finished goods. One thing we did a couple of years ago was to examine US reliance relative to Chinese import reliance. And we know China has a lot, but they don't have everything that they need. So we put this relatively simple matrix to try to understand where do things fall. And so things in quadrant 1 are things for which the US and China are less than 50% net import reliant. Molybdenum falls in the bottom left quadrant because both China and the US are net exporters. Quadrant 2 are commodities for which the US is highly net import reliant, but China is not. So the rare earths, at least as of this writing, in 2014 data, the US was highly import reliant, China is not. Other minor metals like indium, gallium, bismuth fall into that category. The converse of that situation is in quadrant 3. So you have here a beryllium, where the US is the largest producer, and not by accident. There's a significant effort on the part of Department of Defense through the Title III Defense Production Act to make sure that there's a strong and reliable beryllium supply chain. You might be also surprised to see iron and copper in this quadrant. China is a big producer, but their consumption is even greater than their production, so it falls in that quadrant. Quadrant 4 is perhaps the most interesting because these are commodities for which both the US and China are highly net import reliant. So the platinum group metals that are mined in South Africa fall in this quadrant, niobium in Brazil, rhenium in Chile, lithium in Australia and Latin America. Now, you'll notice here, cobalt is sort of in two spots. You might have noticed that there's cobalt with a subscript R and a cobalt with a subscript M in quadrants 2 and 3, respectively. The R stands for refined production and the M stands for mining production. And why they're in different quadrants is because China, while they don't mine a significant quantity of cobalt, they are a major refiner. And we can see that through our data from our mineral yearbooks. What's shown here is from 1980 to around 2018, 2016, world production by country. And you see global mine production for cobalt is dominated in the DRC, but global refinery production is really dominated in China. And of course, cobalt's important because it's used in lithium ion batteries. It's one of the key components in the cathodes. And this is not by accident. If you look at what's going on, a lot of Chinese firms have gone to the DRC and Central Africa to make sure that they have equity stake in those mineral assets and processing facilities so that they're able to ship a lot of that cobalt to China for further refining and ultimately processing and incorporation into lithium ion batteries and vehicles and electronics, et cetera. And it's not just for cobalt. Chinese firms that have invested in mineral assets for niobium in Brazil, lithium in Australia and Chile, rare earths, and of course, Greenland and the Mountain Pass mine in the United States. So that's what China's doing. They're making sure that they're able to secure their resources for their manufacturing sector. You might be wondering, well, what is the US government doing? We do have a standing committee that's been around for more than a decade under the US National Science Technology Council. It's a critical mineral subcommittee that's co-chaired by both Department of Energy and Department of Interior. And it has representation from across the federal agencies. And this subcommittee has really been at the center of a lot of the efforts for the federal government on the executive branch side to help develop a strategy and deliver it. And it's also been following on a lot of the executive orders that have been coming through in the last couple of years. I'll just go through those really quickly. Some of the ones that have come down in the last couple of years, including Executive Order 13817, which really set up the language to suggest that we need to develop a critical minerals list for the United States. That was followed up with the Defense Production Act Title III, five presidential determinations that required the Department of Defense to secure rare earth supply chains. That was in 2019. In September 2020, there was another executive order that looked at addressing the threat of domestic supply chains on foreign reliance. And so that language also in that executive order required that the critical minerals list be updated and reviewed periodically. Even more recently, in December of last year, the Energy Act of 2020, which was part of the omnibus, included a section on mineral security that put into legislation the requirement that the U.S. Provide a critical minerals list and updated every 3 years. And finally, most recently, just in February, the Biden administration put out Executive Order 14017, which looked at American supply chains, including one on critical minerals, but also on semiconductors, lithium ion batteries, or batteries in general, and pharmaceuticals, all of which require mineral commodities. And so there's been a lot of action within the executive branch and the legislation to help resolve some of these issues. One of the central things that our center has been working on is to try to define that critical minerals list. And so this is a publication that we put out in 2020 that try to address, well, how do you define criticality and how do you measure it? And really what we honed in on was to look at supply risk. And here we define supply risk using a conventional risk modeling framework where there has to be a hazard, in this case, a supply disruption, a high degree of supply disruption. You have to be exposed to that hazard and you have to be vulnerable to it. And the idea there is all those components are necessary for there to be risk. And conversely, if you think about it, you need to reduce only one of them for the risk to go away. And so we went about developing indicators for each of those components of supply risk, and we're able to measure semi-quantitatively what the supply risk would be across 50 plus mineral commodities over a decade. And the things that came out on top are things that you would expect: the rare earth elements and cobalt, graphite, antimony, tantalum, tungsten, et cetera. What we also are able to do is identify not only the leading producer, but which applications, which uses are these, is really driving the vulnerability. Now, we're not standing still. We're looking at improving this methodology and updating it. We'll be updating it to include data up to year 2018. hopefully in the next week or so that those results will be published, and they'll directly feed into providing the technical input document for updating the critical minerals list for the US government. We're also looking to enhance the methodology as we are able to do more and more on each of the components. So for the vulnerability component, we're looking at figuring out how can we look at the ripple-on effects to understand how does supply disruption impact the end user and the economy overall. And on the hazard side, we're looking at other hazards. So right now, our focus has been on man-made hazards, right? So political instability in a producing country, but there are other hazards, including natural hazards, which can affect supplies. This is a work we did a couple of years ago, looking at earthquake supply disruptions for copper in Latin America to try to understand, well, what's the expected annual disruption due to earthquakes? You can imagine expanding this. So we are expanding this globally, and we'll have that result hopefully later this year, but expanding it to potentially other commodities and other hazards, natural hazards as well, and ultimately reincorporating that back into our criticality model. Now, once you identify a commodity as critical, what can you do about it, or how can you think about what are ways to reduce it? So as I mentioned earlier, you can reduce any one of those three components. You can either reduce the hazard, you can reduce the exposure, or you can reduce the vulnerability. If we think about just the exposure piece of it, which is essentially our import reliance, right? You're more exposed to it if you are more import reliant. What we can do is we can develop scenarios. So let's take this illustrative scenario. So our domestic demand maybe is increasing, our domestic supply is decreasing. The difference between those is our import reliance or net import reliance. And if we develop different scenarios, we can see, how might that change over time? And then you can develop these wedges to understand, well, how can different tools that are, in our toolkit might be able to reduce that import reliance. So we can develop manufacturing improvements such as 3D printing or near net shape forging. We can develop substitute materials. On the supply side, perhaps we try to increase domestic supplies, a primary or secondary through recycling. Of course, there are limitations to each of these strategies. We can, you can have our Department of State, Department of Commerce work on securing those supplies through trade ties. And what's left over maybe can be secured through government or industry stocks to buffer against any supply disruption. So this sort of illustrative idea is, this is how we can get there if that's our policy goal. The question, of course, then becomes, well, how big are each of these wedges for the different commodities? And they'll be different, right? And so that's one thing that we hope to do. And with the few minutes that I'll have left, I'll just show you a little bit of illustration what that might look like. So we know, for example, this is data from the Energy Information Administration. And this was before the latest announcement from the Biden administration. But we know that solar, for example, is expected to comprise the largest share of globally installed electricity generation capacity. Other things like natural gas will continue to grow, wind will grow as well. But if we think about just solar for a second, we know that there's many different solar PV technologies, the most dominant of which is crystalline silicon that requires silver, for example. Of the other technologies, the thin film technologies, cadmium telluride is the most dominant in the United States, comprising somewhere between 50 to 30% of annual installations in terms of megawatts. And the question is tellurium potentially a bottleneck? So this is something that we're investigating. We pulled together an international group of researchers to try to understand, could you increase tellurium supply, given and knowing that it is a byproduct of copper production? How much could you increase tellurium supply without having to increase copper production significantly? So watch for that coming in the next few months. So quickly to summarize here, so mineral commodities are essential for renewable and emerging technologies. The United States is highly import reliant for a large and growing number of those commodities. As Karen mentioned, import reliance by itself is not necessarily a cause for concern, but it is a component of risk. And when combined with other factors such as production concentration in unable or unwilling countries that might be unable or unwilling to supply the United States and industries that might be vulnerable, you have a situation where there is risk. We've developed this risk-based assessment for the United States. We will use that to update and prioritize the critical minerals list. There is a federal strategy out there that the NSTC Critical Minerals Subcommittee is implementing. And we believe scenario analysis can help us identify which of those strategies will be most effective at reducing both import reliance and supply risk overall for the United States. Thank you.
Thank you very much, Nadal. Great presentation. Excellent. We'll move on to our third presentation. And this is Erez Ishalov. He's the managing director of Traxys Group and specifically a legacy investment arm Traxys Projects and the new battery materials and ESG focused investment arm Traxys Battery Holdings. He's has an LLB from Tel Aviv University and an MBA as well. His prior roles were deputy CEO of a global ferro-nickel group, and he has a focus on investment projects in the metals and mining and metals sector, obviously focused around the emerging electrical revolution. Erez, over to you.
Hello, everyone. It's a pleasure to be here, and it was great to listen and watch the previous presenters, which I think by providing both the more academic angle and the executive arm point of view, kind of allow me to lead it a little bit more to the how we do it on the ground. Traxys is a company that builds and provides services to supply chains, historically to aluminum, to the stainless steel supply chain, super alloys, chemical industries, etc. And in the past few years, I think we kind of saw the writing on the wall, and we realized that green supply chains and a new way of doing things will also require service providers and commodity houses that that work ethically and conscientiously and make sure that that we can help people care and entities care now where things are coming from and where they end. So we that's how we're doing things today, and we shifted more and more towards these materials. Some of them we've been have been part of previous supply chains, but have transitioned in terms of how they are used. This cobalt is a good example. Already, I think 40% or 50% of the cobalt produced every year is used in batteries. And if you scroll back 10, 15 years ago, the number was much smaller, and it was much more of a super alloy and stainless and specific alloy type of material. And we teamed up in the past couple of years with Pallinghurst, which was a legacy mining investment fund, and also transitioned in parallel into investing in the materials that will enable the transition into electromobility and renewable energy. And the way we see it, basically, and I'll dive into the presentation right away, is that in order to really change the world within this century, there are a lot of things that need to happen. And the UN targets are some of them, of course, but we need to plant more trees, release less methane, eat less cows, change the cooling systems in our ACs and fridges, and obviously develop our onboard lithium battery and other storage systems which enable electromobility, clean, green, no noise, no pollution, and the switch to renewable energy. And we asked ourselves, as Traxys, as we do our 10-year plan moving forward, where can we make a difference? And the place where we can make a difference is on the materials. So we chose to focus on battery materials and building the supply chains and investing in the projects that will lead both to primary extraction and to recycling. So invested in a graphite project in Quebec called Nouveau Monde, and a lithium project called Nemaska, and a recycling company called Li-Cycle, and we'll do a lot more. I'll share my screen with you now. And, let me know if it works.
You're on.
Good. Can you see me? Can you see the screen?
Yes.
Great. So I won't repeat that, but as I was mentioning, we're a global commodity house. We've been founded in 2003. Our main shareholder is the Carlyle Group, the blue chip American fund. And the Lewis Bacon funds also have a piece, and there are shares with the management and employees. We have more than 100 partners in our firm. These lithium ion batteries and the materials that are used for them, which are at the moment pretty much all defined as critical materials in all standards. So we're looking at lithium graphite, the NMC, lithium cobalt manganese, and of course copper, which is the most important material for enabling electrification. There's about 4 times more copper in an EV than there is in a ICE, and of course all the charging stations, all the infrastructure. There's going to be a lot more cobalt needed. And then these batteries go into energy storage, the stationary, grid scale, micro, etc. And into the electromobility, the EVs, and but not only forklifts, drones, trucks, and so on. The interesting thing, I think, is that there is somewhat of a circular aspect here, because we will be more and more charging our electric vehicles with renewable energy, or energy produced by renewable sources. And this answers to some of the critique that was heard 5 and 10 years ago when people were saying, what good are you doing when you're driving an electric car that was charged by coal-fired electricity in the back end? To some extent, you're only pushing the problem backwards in the energy supply chain. To my mind, this was not 100% true, because having, getting rid of exhaust pipes with all the effects it has on pollution and health, and just think about the level of noise in some of the city centers and so on. Going electric has a lot of value regardless, but when you combine the two, and you will be driving, you will be moving around on that way, it's obviously a perfect solution. And one of the things that's also developing, but that's part of improvements on grid level, on grid management, and there's a lot of software, and a lot of it is mass data and AI driven, on how you're staying at home because you're only going to work 50% in the office from next year onwards, and you charge your car during the night, and during the day it returns because you're not going to the office on that day, it uploads the power back into the grid. So actually these onboard mobile solutions also act as some kind of a balancing solution for sort of micro peakers, if you will. In terms of growth, everyone was talking about the huge surge in demand and how the supply side will need to answer. So I won't go too deeply into that, but if we're looking at stationary storage solutions and grid solutions, we can see here that there's going to be a huge number of gigawatt hour batteries installed. This is from Bloomberg, and this excludes pumped storage hydro. This is really all the other solutions, and most of them are obviously the lithium ion batteries. And you can see, which is interesting here, and this is something that a narrative that was pointed to before, but we'll see as we continue, that in terms of where the markets are, in terms of installing stationary storage solutions or buying cars, we sort of have China, Europe, North America, and rest of the world more or less equal in very round numbers. Here in this specific slide, the rest of Asia was broken away from China, but in other slides, it's not. And as you scroll to EVs, we see here that we expect within this decade an adoption rate growth from approximately 2.5% last year to about a third of the new passenger cars and light duty vehicles. So at the end of the decade being electric, and most of them will be battery EV, and some of them will still be plug-in hybrids, but not a lot. So these two trends will create obviously a huge increase in the demand for the materials that these batteries are made of. Again, just looking at it from the market perspective, and this will help us when we kind of superposition again everything from the upstream to the downstream. We see that in terms of vehicles sold, again, we have more or less three major markets and the rest of the world. Now going to the downstream and upstream and how these things are made. We see that by the end of the year, Benchmark Minerals, which is the main information collection agency for these materials and for these supply chains, we'll have about 200 gigafactories up and running in the world by the end of the year. We can see that definitely this is becoming part of the mainstream. You see that everyone remembers, I guess, the Will Ferrell commercial from the Super Bowl. And what we can see here is that although, as we saw earlier, the markets are distributed in one way, the customers are where they are. When you look at cell manufacturings and OEMs where these things happen, we see that approximately 75% is in China, only about 5% in the US, and 10% in Europe. And Europe, although it's only 10% at the moment, it's going to grow, and a lot of good brands are already represented there, and more coming into production. But if you look at China and Japan, Korea, mainly, if you kind of add these two together, we're talking about 85% of the production happening in the Asia Pacific supply chain, if you will, while the, call it Pan-Atlantic, is only about 15%. So it's about 50% of the consumer market and installations of stationary storage, but it's only about 30% of the final downstream at the moment. Drilling down a little bit into the materials, I'm sure you'll do more of that in the next seminars with people who are more qualified than a lawyer with an MBA. But basically, the battery has, the two electrodes, the positive cathode and the negative anode, and a separator, which has to be porous to allow the lithium ions to carry electrons from side to side and charge and discharge. The chemistries of the cathode, the popular one that everyone's talking about now is the NMC, which is nickel, cobalt, and manganese, and of course lithium. We'll talk about it later, but lithium in that context is consumed mainly as lithium hydroxide, because in the baking process of the precursor materials, as we call them, we're reaching higher temperatures, and lithium carbonate cannot sustain them, so you need lithium hydroxide. NCA is basically what Tesla is using, and that's nickel, cobalt, aluminum, again with lithium carbonate. And LFP is lithium iron phosphate, which is a cheaper, more stable way of producing the cathode. It's very popular in China. Tesla is actually going to use it for its Chinese Model 3. And people thought it was going to go away in favor of the nickel-rich chemistries, and that within the nickel-rich chemistries, we'll get rid of the 532 and 622 and shift to the holy grail of 811, which means 8 units of nickel to 1 unit of cobalt and 1 unit of manganese. But it turns out that it's not really the case. There are improvements on the LFP. There are improvements on how to make nickel-rich but less nickel-rich type of chemistries. And we'll see later, I guess there's no one size fits all, and it will be depending on the application. An entry-level urban vehicle doesn't necessarily need what a weekend sports car needs, and so on. On the anode side at the moment, the dominant technology is a graphite anode, and graphite is a combination in this respect of natural graphite and synthetic graphite and some silicon. There's an attempt, because of cost and availability, to increase the amount of silicon, but there are limits to that because silicon tends to expand, which causes a problem. So there's sort of a cap at the moment to how much you can use it, and at the moment it's somewhere around 10%. might push higher, but not a lot. And between the natural and the synthetic, the effort is to increase the natural component because synthetic comes from it's a byproduct of oil refining, needle coke basically. But there are also caps on that. Everyone's talking about solid state and the lithium metal anode, but that's going to take a while and is probably going to be again application specific. The most popular electrolyte obviously is lithium ion, lithium in solution, which works in essence as a stevedore carrying the anodes the electrons from side to side. As we look at the supply chain from mining to initial refining and conversion, then making of cathodes, anodes, electrolyte, putting them together in battery cells, and then ultimately into batteries, putting the batteries into the electric vehicles and into the storage system. We'll talk about it in a minute, but what we see that there is a lot of investment and a lot of investment announced on the downstream side, and there's definitely a gap on the upstream and the midstream. Again, this connects a little bit to what we spoke of earlier, so I'll run through this quickly, but this is a map, again, from Bloomberg's research, explaining where in the world are the various chemistry made of. So if you look to the left, you will basically see Tesla with its NCA Panasonic cells in the United States. You will see that in Europe, most of what is made is NMC, and you can see that in China, China and rest of the Asia Pacific, let's call it China, Japan, Korea cluster. They're pretty much making everything and rather dominant on that. What we are seeing now is that because it's not one size fits all, and because there's a realization that you to some extent need to customize your chemistry, not only to the availability of materials, but also to the specific application. There's a difference between a drone, a forklift, a taxi, and a sports car. It's very important to figure out and to optimize relatively quickly your composition and how you're going to get to it. And we're seeing now that there are some interesting startups that are will probably surface later this year that want to provide that angle and enable the producers and the OEMs, the brands, the designers to be able to relatively quickly optimize the recipe, if you will, for the battery that they need for their application or product, and then transition that into design, into procurement, and so on. Again, connecting to the whole narratives. If you just look at the big four, let's call it lithium, graphite, nickel, and cobalt, we see that through this decade, we're going to need to quadruple, if not more, our natural graphite production, and we're going to need another 1 million tons of nickel, class 1 nickel sulfate, or nickel that can be made into nickel sulfate and actually go into a battery. When you see in 2020 343,000 tons of nickel in this graph, this is the nickel that was used in batteries, but 2.3 million tons of nickel are produced per annum. But just the cumulative annual growth rate, which has to do mainly with population growth and infrastructure stimulus, etc., would not take us to this incremental million in 5 years. In 2025, if you add this extra million, we'll have 3.3 million in total. And at that point in time, we'll have more than a third of that already going into batteries. And if you go to the end of the decade, once again, about half the nickel that will be produced at that time will go into batteries. At the moment, it's going mainly into stainless steel. Look at lithium. Lithium is going to need another 2 million tons of LCE by the end of the decade. That's again, five-fold jump. And in order for these materials to actually, for the supply to actually meet the demand, as I think everyone understands, recycling is an important part, and we invest in recycling. but the definition of end of life is not exactly clear because there's an effort made to actually make these batteries last for a very long time. So part of it is scrap in production. A lot of it is electronic scrap, but it's going to take a while before a lot of EVs will retire to a level where they can be substantially recycled. And then, of course, there are all the limitations on what could actually be recovered and how efficient we are on recovering. But it's all part of the same picture. And the good thing about recycling, I think, in this supply chain is that it's happening hand in hand with the growth of the primary resource extraction and conversion. Previously, the primary extraction or primary conversion led to huge mountains of tailings and slag and which were basically left on their own and needed to be managed, and from time to time were tapped with some ideas on how to recover, because a lot of the first extractions was not very efficient, how to do something with them. Some of them are even polluting, some are not, depends if it's vanadium or copper. But recycling was to some extent an after site of sometimes decade after primary extraction, where someone said, look, there's something that's either valuable or hazardous, let's take another look at it. Today, it's totally different. We see that recycling and the whole circular model is growing hand in hand. We saw that the EU already created hurdles for using recycled materials in a growing percentage in this supply chain. And we see that both an independent recycling capabilities are emerging, and let's call it in-house or spin-off recycling capabilities are emerging. So Northvolt, for example, which is going to be a huge cell manufacturer in Sweden and Germany, working closely with VW, they're all already developing an in-house capacity for recycling, which is important. And then again, looking at this disparity between where the customers are, where the upstream is, the midstream, and so on. Just quickly, the lithium that goes into these batteries, if it's hard rock, as we call it, a lot of it comes from Australia. Some of it will come from Brazil when Sigma Lithium opens up next year. This is spodumene concentrate, which basically crushes pegmatites and then concentrates them to a level of 6%. This happens with a again, in terms of efficiencies, if you use only a DMS, what we call, it's probably 60–70% recovery. If you also crush everything and float, you can reach probably a 90% recovery in terms of what you're leaving and what you're leaving as a slag and what you're recovering into spodumene. But again, that's a trade-off because crushing requires energy and flotation requires consumables, and there's always a trade-off there. Then the 6% material needs to travel to another part of the world. Typically, it goes from Australia to China, where it's further converted mainly into lithium hydroxide in chemical plants, and then the lithium hydroxide, or if it was lithium carbonate, can go into a cathode. In Chile and in Argentina, it's mainly it's brines, which are pumped and historically evaporated in huge evaporation ponds for many years. But now there's an effort to work on direct extraction of lithium, which basically means you filter the brine relatively quickly and return it back to the salar, which is basically a salinated aquifer. And so there's a lot of tech work, and we're talking about all kinds of improvements that can also make the supply chain more efficiency. So it's not only primary and recycling, but also new technologies and better ways of doing things. So potentially in the lithium triangle of Chile, Argentina, and actually Bolivia as well, these technologies, and it may also reflect on the lithium basin in Nevada, will perhaps allow tapping more resources that at the moment have their environmental and water balance issues. nickel, again, nickel, most of the nickel, some of it comes from the north, from Canada and Russia. That's the primary nickel sulfate mainly. But most of the nickel is still at the moment that's mined is the laterites. Indonesia and the Philippines are the biggest ones. In Indonesia, historically, they were just mining and shipping nickel laterite ore, which has about 35% moisture and only about 2% nickel. Talk about moving around a lot of waste and a lot of water. And that also has a carbon footprint, obviously. Now, since 2014, there are rules that require an increased component of local production. So they are producing the nickel pig iron, which goes mainly into stainless steel. And Tsingshan, the Chinese producer, has announced recently that they developed a way to convert NPI into nickel matte. And nickel matte is something that can be converted into nickel sulfate, which is ultimately what you need in a battery. But Australia also produces some nickel, and in essence, what you need in order to go into a battery is nickel sulfate, the nickel salt. The easiest way to make it is from a hydroxide, nickel hydroxide, or MHP, which is mixed hydroxide precipitate, also has some cobalt. We see now the emergence of some independent nickel sulfate producers, which basically want to rely on buying nickel hydroxide or MHP, converting it into nickel sulfate, and then selling it to the cathode manufacturers. Cobalt, again, as was mentioned here before, the DRC is very dominant. Had some issues that had to do more with ESG. The material in terms of quality and quantity is obviously very good. Most of it is converted then in China. So cobalt hydroxide becomes cobalt sulfate mainly in China. And you can also take cobalt metal and dissolve it into cobalt sulfide. Natural graphite is mined, crushed, concentrated, and then it's a high-grade concentrate. It's in the high 90s. So when you actually move it as a concentrate, you're moving a lot of material because it's a material that you need a lot of. It's the biggest battery material, but in terms of at least efficiency of moving the concentrate, you're not moving a 6% material or a 32.5 material in weight if you're looking at manganese and so on, but you're actually moving something that's highly that's more concentrated, which is a little bit more efficient and has a lesser footprint in terms of carbon emissions associated with just moving a lot of things from side to side around the world. Here, just looking again at the where things are mined, where things are produced, and where things are ultimately consumed. We can see again that most of the anode, cathode, and materials that go into them, the conversion happens in the Asia-Pacific supply chain, if you will. And we see here in the Pan-Atlantic, whether it's Europe or the North Americas, that it's a much smaller component, but it is growing, at least in terms of the downstream. Then, sorry. Here we have, again, from Benchmark's really great research in their recent presentation. They're actually showing how things move around and where there's the extraction of the key material that happens, where there's the chemical processing here, where do you put it into an anode or a cathode or a cell, and where do you actually make the applications, a car for that matter, and use them. And again, when we see with the same picture, if you look at it for a minute from a US-centric perspective, we're about 25% of the markets, and we're very little of the in-between. We're somewhat more represented, and will be somewhat more represented on the downstream, on the gigafactory part, and the assembly, actually putting these cars together, but very little chemical conversion happening at the moment, and very little extraction, nearly nothing, and everything that's along this critical path. Something to think of is that a lot of these resources are actually available in Canada, And we as Traxys are investing in Canada, and we do see a good opportunity to develop a combination of upstream and midstream conversion between the US and Canada. And we also see a pan-Atlantic narrative where between Europe and between North America, there could be a lot of synergy and a lot of cross-pollination. And I'm not talking about this from a political perspective, but from a practical perspective of trying to keep the supply chains short, just in terms of the various risks that have to do with collecting materials from a lot of countries, moving them around a lot of places, and the inefficiencies of and then carbon emissions of the process. And then I think we can hop to our main conclusions and mainly points to think about. So we see that the rapid adoption of EVs and the deployment of stationary storage will create a huge increase in demand. And we're asking ourselves, how will the supply side respond? There is no avoiding massive expansion on the primary production. That means we're going to need to extract, meaning to mine, all these materials, and quite a lot of them. But we're going to have to do it in better ways than was done in the past. And just giving an example, and again, I'm not objective because we invested in Uvamon Graphite, but one of the reasons we invested in them is because they will be using a electric yellow fleet to mine. They will be drag stacking their tailings in a very safe way, and they will be using hydropower for their purification process. So they're basically a carbon neutral process, making anode graphite, natural spherical coated anode graphite. And this can happen with other processes as well. So the thing is not to stop extracting or to avoid it. There's simply not enough material in circulation for us to say, that's it, we're stopping and we're only going to recycle. We need a lot of investments, and we need a lot of new projects actually happening on the chemical conversion plant side and on the mine side. Recycling, definitely important, definitely something that we need to do a lot more and to get better and better in doing. And just like anything else, the graph that was shown earlier about the diminishing efficiency as you run from from what you insert into the supply chain into what you actually reuse again. Hopefully these percentages will get better over time. And what will enable that will be technological advances, efficiencies, learning curves, and so on. It's a young supply chain. It's a young process, and I'm sure we'll get better and better in that. To add the fourth dimension into all of this, just to understand, we're talking about all these growth patterns on the demand side by the end of the decade. It takes at least 5 to 10 years for a mining project to actually reach its commissioned capacity, sometimes even longer. It takes 2-3 years to license and build and stabilize a complicated chemical plant. So we need to start doing it now, or rather, we should have started a few years ago, because at the moment, availability of materials is really perhaps the only cloud that's kind of casting a shadow over this and can potentially rain on our parade. I think people's hearts are already probably in the right place. The executive is definitely on board. There's an academic consensus, regulations are in place, legislature, everything that you need is there. And I'm really concerned that the materials will not be there if we don't move quickly. We see that there's a lot of investments already and a lot of investments announced in the downstream, but really not enough on the upstream. You would have thought that there would be a gold rush and everyone would rush to build nickel mines and expedite any plans for building the graphite projects and lithium projects, but it's not happening as fast as we would like it to happen. Talk about capital intensity. We're talking about big amounts here. Just to give an example, if we need 2 million tons more of LCE, of lithium grade, of battery grade lithium, the capital intensity, if you go through the hard rock route, is something like $25,000 per annualized ton. So that's on its own about $50 billion. Even if you space it over a few years, we're talking about a big amount. Nickel, capital intensity for nickel, and if you need another 2 million tons of that, it depends on the methodology. It varies substantially, anything from $20,000 to $120,000. But if you just use 50, then you see that you're at $100 billion, and so on. Graphite and copper are potentially less capital intense, but we need we need millions of tons of more copper. So really, the world needs to start investing, and to start investing rather quickly. Another observation we had, and I think it went across all three presentations, I'm sure you'll be talking about it more, is that if you superposition all the maps, you will see that the upstream is in one place, the midstream is in another. The markets are distributed sort of more or less evenly between the three parts of the developed world, and that creates its issues, challenges to the supply chain. And companies like Traxys, what we do is help sort of grease these frictions and smoothen these things and enable these supply chains to move as efficiently as possible, and avoiding situations where materials arrive too early or don't arrive at all, or there's all kinds of timing and sequencing issues. There's a lot of working capital involved. We were just talking about the capex, but there's a lot of that as well. And so Traxys and companies like Traxys provide the liquidity to some extent to connect the various links in the chain. Again, as this supply chain develops and seeks to find the best practices of anything and everything that's done there, a lot of the processes consume a lot of energy, whether it's crushing, calcining, thermal purification, and so on. So using renewable energy sources to actually provide energy to these parts of the process is important. And that's something that we see already in Scandinavia and on both sides of the Niagara Falls, but I assume we'll see more and more of that. And perhaps in other areas of the world, it's going to be more solar, more PV, but that's very important as well. And then last but not least, some of these processes are, let's call it complex from a chemical perspective. If you take nickel, for example, you need to sulfurize your nickel. You take a nickel hydroxide or a nickel metal, and then you turn it into a nickel sulfide. But then when it goes into the cathode, it has to be hydrated again. So it's desulfurized, and then you have a sulfur waste at that point, which you need to recycle whatever you can and dispose of what you can't in a safe way. And that's true about pretty much all the others. So once again, if you can either avoid some of these processes, make them more efficient, or just make them more regional and localized, so you move less hazardous materials, or you do that for a shorter period of time and less kilometers, that's also very important. And that's it. That's a wrap.
Okay, thank you very much, Erez. Very nice presentation. We've got a lot of questions coming in, and I guess just listening to the three presentations, we're clearly on the startup ramp-up curve, whatever you want to call it, of a major energy transition. And I guess what's really unusual about it, to me anyway, is that it's a massive transition on the electricity supply side, but also on the demand side, on the end use, and this shift to EVs, and of course the requirements for storage and large grid scale energy storage and micro scale energy storage. And clearly those are the factors that are going to be driving these metals and minerals requirements. I'm kind of left wondering if there's still a massive disconnect in an understanding of the quantities of some of these metals and minerals that are going to be required, and whether we've done enough or are doing enough to quantify it. But I guess I'll jump to a couple of the questions because we've got some really good ones. The first one I think is for Nadel, and it's on phosphorus. And several people on the chat have asked about phosphorus. Does it mean more phosphate mining? Is there more phosphorus required in the EU versus the US? Maybe Nadel, could you jump in, and Karen, if you want to add?
Sure, I'm happy to. So I think if I'm looking at the question, I think there's often an equivalence of importance with criticality or supply risk. And I think that's what we've sort of tried to avoid at the USGS, to say, okay, all the commodities are important to somebody at some point, but is it critical? Really for us means, is there a supply risk? And phosphate rock is obviously very important. We really can't live without it. For the United States, it's not on the critical minerals list for the United States, unlike it is for Europe, for several reasons. One is that the US is a major producer. There are at least 10 mines in the US that mine phosphate rock, and we are less than 10% import reliant on it. And there are many, many producers throughout the world, especially in North Africa and West Asia. And so we see it as less of a concern for the United States. Not to say that it's not important, it's obviously important. And I think another part of the question was, could you reuse or recycle it? I think it's, potentially, but I think at currently it's quite difficult, mainly because it's lost during use, right? So, and a lot of the environmental impacts that happens, like eutrophication, is because of that. We're not really collecting it after use. And so I think, there are some things that you can do a good job recycling, but economics and ultimately thermodynamics plays a role in whether you're going to recover and recycle some of this stuff. I haven't studied the issue specifically with lithium iron phosphate batteries. Is that going to increase demand for phosphate? I would imagine that it will obviously increase it. Is it significant? I don't know relative to the market of phosphate rock. It's about 220 million tons produced annually. It's quite a large market in comparison to some of these minor metals that we're talking about. Is it going to make a big dent? It's not clear. LFP is really just now used in China, mainly for buses because of the safety concern. But also now, as was mentioned, more in passenger vehicles, but still in China, where it is a lower performing battery. So it's not clear to me. It's something that perhaps should be studied, but I don't have additional information on that.
Yeah, thank you, Nadel. Maybe I can go to the next question for Karen if you have any other comments on phosphorus. But the next question is really for you, and it's are there new opportunities in critical minerals, rare earths production in places like Greenland?
Yes, I was very, very happy to see that question. The last picture I showed was actually a picture from Greenland, not from a rare earth deposit, but from a palladium deposit. But I've worked on some of the rare earth deposits in Greenland in my past. And it's a great question because it sparks a couple of interesting things that we can bring into this discussion. Because a really important thing, of course, to understand about rare earth elements is that they're not actually rare. And so the abundance of rare earth mineralization is enormous and far, far, far greater than our need for the next many centuries, to be honest. So it is actually it's a good example of criticality because it has nothing to do with geological availability at all. It is a very, very thin market. It's about as abundant geologically as copper, but we're using, orders of magnitude less than we're using copper. So it's a very small, thin market. That is one of the things that makes it critical. And then really importantly, the value chain again. It is not so much digging it out of the ground that's the problem here. It is actually processing the minerals into the metals that we need for our technologies. It is incredibly complex relative to a lot of other more sort of, say, pedestrian commodities. So it's very complicated. It actually turns out that almost all of the downstream, so taking the rock and converting it into something that we can put into our things, almost all of that happens in China. And that's why it is so important that we focus. Well, of course, we need to have expertise in certain parts of the value chain, but we really have to zoom out sometimes and make sure that we integrate the knowledge of the entire value chain, because the problem with rare earths is much more related to the downstream processing than to the actual mining. And while Greenland could turn into a rare earth mining nation, they probably would not have the capacity, just sheer sort of lack of population and infrastructure, to be able to do any of the downstream processing. So the current projects in Greenland actually have, as part of their plan, to ship almost all of it to China for downstream processing. So that's one reality. Another thing I want to just pick up very, very briefly that also connects to this is when Eris was talking about how long time does it take to open a mine. For most mines, actually, it's even longer than Eris was suggesting. For many mines, it takes decades from you have a discovery until you can actually develop it, maybe 15, 20 years at the best. And rare earths there are particularly slow in the upstart because of this very complex metallurgy that is unique from each different occurrence. You have to basically reinvent the whole sort of downstream processing. So that is, those were important facts about rare earths.
Great answer, Karen, very nice. So next question, perhaps can pass this to Eris to give us some comments on. One of the challenges facing producers and on the supply side is how to project prices for these different metals and minerals in the future. And the challenge being, if the demand isn't firmly established and there's insecurity of whether technology is going to go one way or another, how does that affect producers' ability to plan forward and justify what may be very large, lumpy capital investments to bring more supply to market?
True, there is indeed what we call the incentive price projection of taking of adding supply, but we are at the point today where I think it's consensus is that you can already rely even on the of the lower end of the curve in terms of projected adoption rates to justify adding quite a lot more supply and capacity. The risk that that someone will end up building a nickel mine that produces ultimately 20, 30, or 50,000 tons of nickel per annum, and end up without a response from the demand side at the moment seems rather low. It looks like we may not see the prices we saw in 2007 of 50-something thousand tons of $50,000 per ton of nickel, perhaps even ever again, and some of the of the spikes that we saw with cobalt historically, with copper and so on. But I think there are really, really good and strong signals from the demand side that a lot of people are crossing the point of no return in terms of their commitment to investing in the downside and transitioning to a level where they will need these materials. Current supply is not enough. Current recycling is not enough. There's need for a lot of supply, and we're still far from a point where all kinds of marginal projects need to decide if they're hopping on or not, and they might end up, missing the bus or being the guys that are in the highest cost quartile of the cost curve. There's a lot of work to be done still in the first, second cost curve quartiles to bring on board and online good projects that will have customers. They they will be economical. They will make money for the shareholders and for the other stakeholders. And really, the message
Great.
at the moment is that we have to move forward. Procrastinating is only going to cause damage.
Yeah, great response. The next question is really for Karen, and maybe it's a very specific question, but maybe you can broaden it to the general issue of the circular economy. But the question was asked about these wind turbine blades, which has been in the press lately a lot about the inability to recycle them and where they're being disposed of. And of course, wind power is probably not going to be as much as solar in the US, but it's certainly going to be a massive portion of the renewable energy component.
Yeah, I think, again, an excellent question, because it really sort of puts the finger on one of the problems with this. I want to call it actually greenwashing, when we just sort of put on a green circle and say, you know, we can recycle it and then everything is good, because the whole sort of recycling thing is extremely complex. For another good example, to broaden it a little bit, is that a lot of companies have looked at lightweighting of cars and other airplanes, trains, these kinds of things, because if you make transportation lighter, you save energy. So this is really green, right? We all like it. That's a great idea. But it actually turns out that most of the lightweighting you can do to a vehicle will make it harder to recycle. The best thing would actually be to build the whole thing out of steel. We're really good at recycling steel, but then it's extremely heavy and it gets really, really poor mileage. And it's a little bit the same with the wind turbines. It's like, you know, it's unfortunately, the complexity is such that once you do something that is green in one aspect, it many times has some other aspects to it that we need to solve. And it's also a little bit back to this thing of, you know, if for instance, we all think we should recycle these, right? And we should get all of the metals out of them. But what if it takes more energy to recycle gold out of this one than out of my rock? Which is the right one to do? And also, if we do, for instance, extract gold out of this one, we leave behind the other 55 metals that are in there, because they're in such small quantities that it would be basically impossible to take it out. So this thing of lack of recyclability is a real challenge. And I think that what will most likely have to happen, and I think companies are already really struggling to do, is actually to try to start getting better at designing for recyclability, knowing that sometimes that will affect how well suited a material actually is for what it's doing. Again, back to sort of electronics, you know, alloys are just optimized for that performance that we need to have. Maybe it's time that we sort of say, well, you know, we are willing to be a little bit flexible on the performance side if, on the other hand, we can actually recycle it. So I think that we'll see a lot of work going into development of new blades, new types of blades for wind turbines, because that is going to have to be solved.
Great. Yeah, really good. And we've got a lot of questions coming in. There is no way we're going to get to all of these in the time available, but I'm going to move right along to a question for Nadel. And thank you everybody for your questions. These are great questions coming in. The question, you discussed executive orders and some of these things that have been made in the US recently. And the question is, you know, well, that's fine, but what's being done with those? How is this helping to shape the response within the industry and in the country in general?
Sure, great question. So there is a federal strategy out there. It was developed by the Subcommittee on Critical Minerals and released by Department of Commerce. It has 6 calls to action that range from everything from, you know, doing research and development to, you know, having better mapping of the United States to understand where these resources might be, to, you know, having a more aligned workforce, you know, with actions for both NSF, National Science Foundation, as well as Department of Education. So it's a wide-ranging federal strategy, and you know, it's just being implemented. And I think just as the trend for that we've seen, where mineral commodity production has shifted overseas, has taken decades, we're not going to be able to solve this problem within a year or two, right? It's going to take us a concerted effort over many, many years to be able to really turn things around. So I think, the criticism is there. It's like, well, what have you really done? But I think, we're moving in the right direction. Is it fast enough? Could it be faster? Possibly. But these things do take quite a lot of effort and a lot of time.
Yeah, great comment. I think we've got a question from a committee member. Jim, did you have a question?
I do. There's fascinating conversation and presentations today. Wait a second, okay, there I am on. So what I was wondering, and would love to get some feedback from the panelists on, when you look at other energy markets, oil, natural gas, coal, we have a phenomenal, robust system of tracking supply, demand, and future outlooks with the International Energy Agency that does it for the OECD and the world, and the Energy Information Administration, which is the U.S. agency that does the U.S. and the world at great detail. And so it just strikes me that are we moving to an area where we really ought to have either within existing or create new statistical agencies in the U.S. and the world that could be dedicated to track the supply, demand, and outlooks for these minerals, because it's nothing against. I think there's still a huge role for consultancies and others that track these things. But the difference with things like the EIA is the ability within the government context to do surveys of all the supply and demand entities out there, and then combine all that data. So just, are we at a point where we really ought to look at this in a much larger fashion? And that might go to the question on communicating the important aspects of this more broadly.
I can maybe jump in first.
Yeah, go ahead.
I mean, that's a central mission of our center at the National Minerals Information Center at USGS. We've been doing it for over 100 years. It's part of the Organic Act, and really the forward-looking piece is now in legislation with the Energy Act of 2020. So we do track it. We track 90 plus mineral commodities over 100 countries. It is difficult though, because a lot of these commodities are very small markets, right? And a lot of them are opaque markets where the information is not readily available. It's not necessarily shared. It's a lot of times there's no market prices. They're not traded on like the LME. And so there's very little information about what is going on with these commodities. And a lot of the problem that we have is that while we do send out tens of thousands of surveys, it's all on a voluntary basis. So companies, domestic and international, choose or choose not to respond to our surveys to collect this information. So that's part of the problem. I think the bigger part is that there's just small niche markets that a lot of the industry players are, it's part of their competitive advantage, and sharing that information is just not something that they're willing to do.
And
yeah.
Claire,
May I?
go
Karen?
ahead.
Go ahead, Karen.
To follow up after you.
Yeah, I'd like to come in as well. So actually, this thing about the mineral statistic, BGS also does this, and we do it with a slightly different methodology. And you'll all be happy to know that we actually sort of arrive at compatible answers, I'd say, or aligned answers with USGS, and also, of course, communicate about it, because it's always reassuring when two slightly different methodologies arrive at similar answers. But I also think it was an interesting question today, because earlier today and for the rest of the week, I am participating in the United Nations Economic Commission for Europe, which includes North and South America, by the way, Resource Management Week 2021. And it is actually an attempt to coordinate how we deal with resource management on a global level. And one of the things that this program this expert group sets out to do is to introduce a UN framework classification program for mineral resources. And this has actually worked for energy resources, where we measure them the same way and we talk about them the same way on a global scale. And there is now this huge initiative coordinated by the UN to try to come up with a framework classification that works for minerals. It is much more sort of, they're much more heterogeneous. Oil and gas, there's a limit to how variable that actually is going to be for you, but minerals are extremely variable and there are very many different kinds. So it's a little bit more complex, but it is actually work in progress, and it's work that's leaning on some of that information and knowledge that's being collected by, for example, USGS and also BGS.
Jim, you want to go ahead?
I was just, yeah, I fully acknowledge the complexity. And Nadel, what I'm thinking is that is actually to help raise your profile in what you're doing, so that you have a little bit. I think the EIA, when they do surveys, they have some teeth on that, on the expectation of people replying to them, and also on the keeping the data, the ability to keep all that data confidential and aggregated. So, and recognizing that with thin markets, it's tough. There isn't sometimes enough to aggregate for that. So I get all that. I would also be interesting in Erez's thoughts on that, because he comes from a kind of that consulting, kind of tracking information point of view.
Yeah, we as a global commodity house, we can we also have obviously our information sources and our ability to partially, of course, track some of these materials and trends, and kind of have our own projections on supply and demand, at least in the very short term and the very long term. And one thing that is pretty apparent, as I think Nadel was saying, with some of these products, these are not really commodities. And some of them that are commoditized and even traded in a market, in a terminal market, as we call it, like the LME, are not very liquid because they're just too small and too concentrated. So this adds to the complexity of accumulating data and statistics. And there's a whole debate about what exactly is battery grade in pretty much all of these materials from the field, from the people that actually need to take something and convert it into whatever is the next link in a chain, to a level where last year there was even some discussion in the lithium space and one or two of the other materials, the guys that were buying it to make cathodes and anodes were saying to the intermediates, those sitting between them and the mines, you know what, don't give me battery grade, because it's not really battery grade. I still need to clean it, even if it theoretically meets the spec, or do some work on the sizing and so on. Hold short a little bit before that. Give me clean enough industrial grade or technical grade, as long as that there are no hazardous impurities and everything is sort of under control. We will actually do the final refining before and tweaking before we introduce it into our electrodes. And part of it might be a bit of an IP issue, because then they can keep it more as a secret sauce. Part of it had to do, I think, with pricing and with the fact that many times you ended up with material that was rejected because it wasn't meeting the spec. They started arguing about who has to pay the cost of doing the final cleanup and so on. So I guess this also reflects on the fact that it's an industry still, if not it's in its real infancy, still it's a toddler stage, and and there's a lot will be learned along the way as it improves and expands, and the back and forth between the markets and the various links in the supply chains will ultimately lead to some kind of a direction. And just scrolling back for a brief second to the first question, from a materials perspective, no material wants to cost so much that everyone would make a huge effort to engineer it out of the supply chain. So from that perspective, You know, you might think that you know, people who control cobalt would want it to be at $150,000 a ton, but it's not exactly the case, because then the efforts to make batteries without cobalt or with less cobalt will increase. And we saw that in nickel just before the global financial crisis, when nickel was reached 50,000. The stainless steel guys invented the 400 series without nickel. So you don't want to be there. You want to make enough money, but not too much money, and everyone should, you know, should fairly share the pie somehow, and everyone grows together. Otherwise, it's just not sustainable. And all stakeholders need to enjoy. And it's sort of a global Kaizen, I guess, where everyone plays his role gradually over the next few decades. And hopefully we'll get there, or our children will get there.
Thank you. Great. That's a great wrap up, Erez. Really appreciate that. Good concluding remarks. Maybe just give Karen and Nadel maybe 30 seconds each for some concluding remarks, and then we're at our time limit. Karen, would you like to?
Yes, that took me by surprise. I didn't expect that. So now I get to talk again.
30 seconds.
Yes, 30 seconds. I just want to say again that I think the really important thing is again to understand the complexity and not have it be a value game. It's almost a little bit as if there are people that are against mining and the ones that are for mining are sort of bad people who want to hurt the environment. And we need to make the discussion much, much more complex than that. And we need to take the discussion to a very, very broad audience, the general public, the decision makers. And that is probably best done through really a lot of education and a lot of sort of targeted conversations about the complexity, and acknowledging that, again, yes, if we want a wind turbine, we're going to have a problem with the blade. Yes, if we want to do this green thing, we're going to get a problem with that. And let's, instead of sort of pointing fingers and being good and bad, let's talk about solutions.
Great.
I completely agree with Karen. This is a absolutely correct point. I think maybe stepping back a little bit, this is one of the biggest transitions that's going to happen with this energy transition, as you mentioned, John, both from the supply side for electricity, but also on the demand side, the use side. And non-fuel mineral commodities are going to play a key role in that. And I think the big question is, how are we going to be able to meet that demand? And is the U.S. and other developed countries going to have a significant role, or are they going to be more of the users of these supply chains that are going to probably last for many, many decades and really transform the world? And so there are, I think, targeted things that can be done to alleviate some of these risks that can and help fulfill some of that demand. And I think there's no single silver bullet. You'll have to look at recycling. You'll have to look at new developments. You'll have to look at alternative materials. But I think the key question is, which of these strategies or tactics is going to be most effective for which commodity? And that, I think, needs to be understood better.
Great. Well, that's excellent. I'd like to say thank you to our three speakers, Erez, Nadel, and Karen. You did an excellent job, and it was great discussion. We could have done with another hour at least. And there are a lot of questions I'm sorry we did not get to. There are a few of those that I think are going to be addressed in the next two webinars, several in particular that I see related to public perceptions and those sorts of things, and regulatory environmental climate. So thank you to the NASEM staff and the rest of the committee. And we'll look forward to seeing everybody hopefully on May 17th for the second webinar. Hopefully all of you can make it. And thank you all for your participation. Bye-bye.
Thank you.
Thank you.
Thank you.
Thank you.